The ground in northern Iraq does not give up its secrets easily. It holds them the way old stone holds heat, slowly, reluctantly, in layers. For centuries, the mounds that rose above the flat plain between the Tigris and Euphrates were simply features of the landscape. Farmers built around them. Traders navigated by them. Nobody looked beneath them. Nobody thought to. Then, in the winter of 1849, an Englishman named Austin Henry Layard knelt in the dust of one of those mounds and began pulling objects out of the earth. They were small and hard and the colour of dried mud. They looked, at first glance, like broken roof tiles, fragments of something domestic, something thrown away. But Layard had seen enough by then to know that nothing in this ground was random. He kept pulling, his team kept digging, and the tiles kept coming, thousands of them, then tens of thousands, filling baskets and crates, and eventually entire shipping containers bound for London. They were not tiles. They were tablets, objects pressed from wet clay and left to harden, each one carrying on its surfaces a dense field of small wedge-shaped marks arranged in rows. Some were the size of a hand. Some were smaller than a palm. Some were cracked straight across, as if someone had tried to break them deliberately. Most were not. Most had survived intact through 3,000 years of darkness and compression, sealed beneath collapsed rooms and rotted timbers and centuries of wind-driven soil. Hold one of these objects in your mind for a moment. Feel the weight of it, heavier than you would expect, denser than modern fired clay. Run your fingers across the surface and feel the marks, not drawn, not carved, but pressed. Each one a small triangular depression left by the angled tip of a reed stylus. The reed is long gone. The hand that held it is long gone. The city that surrounded the act of writing is long gone. But the marks remain, sharp and clear and entirely legible to the right eye, as precise as the day they were made. Layard's team had no such eyes. They catalogued what they found as best they could, crated the tablets in the same shipments as wall reliefs and bronze statues, and sent them to the British Museum, where they filled room after room and spilled into corridors and sat in storage for decades, while the scholarly world slowly, painstakingly learned to read them. The process took generations. There were false starts, wrong guesses, brilliant breakthroughs followed by long silences. Decipherment is never fast. It is the work of lifetimes. What the tablets contained, when they were finally opened to human understanding, was something the world was not quite ready to receive. Not because it was mystical or supernatural or deliberately hidden. It was none of those things. It was stranger than any of that. It was ordinary. It was administrative. It was, at the surface level, breathtakingly mundane. Lists of grain, records of wages, receipts for livestock, temple inventories, royal decrees. The ancient world, it turned out, ran on paperwork, or rather, on claywork. And there was a lot of it. But paperwork is only the surface. Beneath the administrative layer, buried in the quieter corners of the archive, were tablets of a different kind. Tablets that someone had pressed not to record a transaction or mark a boundary, but to think, to calculate, to solve a problem and record the solution in a form precise enough that someone else could replicate it exactly. Tablets that recorded not what was, but what must be, the results of careful, patient, rigorous computation. These tablets did not look different from the administrative ones. They came from the same clay, were pressed by the same kind of reed, were stored in the same rooms. But what they contained was of a different order entirely. These were not the records of a civilization. They were the architecture of one. There is an official story about cuneiform. It appears in textbooks, in encyclopedias, in the introductory panels of museums' exhibitions. It is not wrong exactly, but it is shaped in a particular way, arranged to reach a particular conclusion, and that arrangement leaves certain things quietly out of frame. The official story goes like this. Around 3400 BCE, in the city of Uruk in what is now southern Iraq, a system of recording emerged that would eventually evolve into one of humanity's first true writing systems. It began with pictures, simple representations of objects scratched onto clay tokens, a circle for grain, a cow's head for cattle. Over centuries, the pictures became more abstract. The tokens became tablets, and the scratches became wedges. By around 2600 BCE, the wedge-shaped marks, cunei in Latin, hence cuneiform, had been organized into a flexible system capable of recording not just objects but sounds, not just things but ideas. It was a great leap forward. Civilization, in a meaningful sense, had begun, And what did this civilization write about? The official story has an answer for that too. Commerce, administration, trade and taxation. The grain stores of the temple, the rations issued to workers, the land transactions between merchants, the tribute owed to kings. Cuneiform was invented, the textbooks explain, to run an economy. It was the spreadsheet of the ancient world, the accounting software of the Bronze Age. This is true. There are literally hundreds of thousands of tablets that prove it. Cuneiform was, for most of its history, used by most of the people who used it to count things. The ceiling of this story is low. Under its arc, the ancient Mesopotamians emerge as clever administrators, skilled farmers, competent builders. They organized labor and tracked grain and built cities in the desert. Admirable things, by any measure, but nothing that demands a revision of how we think about the history of human intelligence. Nothing that would require us to look again at what we thought we knew. Then the scholars moved beyond the administrative tablets. They moved into the mathematical ones, and the story the textbooks had told began to feel like a room whose walls were closing in. Because the mathematical tablets did not behave the way the official story predicted. They were not rough. They were not approximate. They were not the arithmetic of farmers estimating yields and merchants settling debts. They were something else. Something that the standard vocabulary of ancient history did not have comfortable words for. The numbers were too precise. The procedures were too structured. The logic was too clean. Someone working in dried riverbed clay with a cut reed had been doing something that bore an uncanny resemblance to what a later age would call computation. Not computation in the casual sense of adding numbers. Computation in the architectural sense. Systematic, reproducible, formally organized operations on structured data, producing defined outputs from defined inputs. The kind of thinking that, in another era, would require a machine. The official story did not collapse in the face of this. It absorbed it quietly in the specialist literature and continued as before. The textbooks were not updated. The museum panels were not rewritten. The introductory chapters kept describing cuneiform as an accounting system, an administrative tool, the bureaucracy of the ancient world. And technically, they were not wrong. Cuneiform was all of those things. What the story left out was what it was also, quietly, persistently, in the mathematical tablets that sat in the same archives as the grain receipts, waiting for anyone paying close enough attention to ask the right question. Somewhere in the collection rooms of Yale University, in a cabinet among thousands of other ancient objects, there is a small clay disc. It is not impressive to look at. It fits easily in one hand. Its surface is worn at the edges, and some of the marks on it have faded almost to invisibility. It was made, by the best current estimates, sometime around 1700 BCE, before Rome existed, before the Greek alphabet had been invented, before the concept of zero had been formally named by any recorded civilization. On one face of the disc, someone drew a square. They drew the two diagonals of that square. Around the figure, arranged in careful rows, they pressed a series of numerical marks. Scholars catalogued this tablet, studied it, photographed it, and eventually published an analysis of its contents. The analysis was startling. The numbers on the disc are an approximation of the square root of 2, the length of a square's diagonal relative to its side. The approximation is accurate to 5 decimal places. Written in modern notation, 1.41421. Think about what that means. The square root of 2 is an irrational number. It cannot be written exactly. In any number system, in any base, in any notation, it goes on forever without repeating. To approximate it to 5 decimal places in the modern system requires either a calculator or a very careful procedure applied many times in succession. You start with an estimate. You refine it. You refine the refinement. You keep going until the result is close enough to satisfy whatever standard of precision you have set yourself. This process is iterative, convergent, and mathematically rigorous. It is not the kind of thing you stumble into. It is the kind of thing you design. The person who made this tablet, whose name we do not know, whose face we cannot picture, who lived and died in a city that no longer exists, had designed exactly this kind of procedure. They had applied it carefully, converged on a result accurate to 5 decimal places, and pressed that result into clay with the calm confidence of someone recording a fact rather than an estimate. The disc does not show the calculation. It shows only the answer. But the answer is too precise to have been guessed. It was computed. This tablet, catalogued as YBC 7289 in the Yale Babylonian collection, is not unique. It is one of hundreds of mathematical tablets recovered from Mesopotamian archaeological sites over the past century and a half, each one carrying evidence of a level of mathematical sophistication that sits awkwardly in the standard narrative of ancient civilization. There are tablets that solve quadratic equations, tablets that list Pythagorean triples with a precision that implies a generative formula rather than trial and error, tablets that model the motion of planets using arithmetic procedures that remained the most accurate in the world for nearly 1,000 years. The anomaly is not hidden. It is sitting in museum collections around the world, catalogued and photographed, and available to anyone who knows to look. The anomaly is simply that it has not been named. Not in the textbooks, not in the standard histories, not in the popular accounts that shape what most people know about the ancient world. The mathematical tablets of Mesopotamia are described as impressive, as ahead of their time, as evidence of a sophisticated culture. What they are not described as is what they actually are: a record of systematic, procedural, formally structured computation. Computation that predates the word, the concept, and the machine by 4,000 years. The question that this disk poses, this palm-sized, worn-edged piece of fired clay with its 5 decimal place answer, is not a question about ancient history. It is a question about the nature of computation itself, where it comes from, what produces it, and whether the mind that reached for it in a river valley 4 millennia ago was reaching for something it understood or something it had, in some precise and quietly remarkable sense, invented. To understand what the tablets might contain, it helps to understand what they are made of. Not in the chemical sense, but in the structural one. Cuneiform is not a writing system you can approach the way you approach a foreign language, looking for equivalent words or familiar patterns. Its architecture is different from anything in the modern world. To read it, you have to first understand how it was built, and that understanding begins not with meaning, but with touch. The word itself is a description of a gesture. Cuneiform comes from the Latin cuneus, meaning wedge. A cuneiform mark is a wedge, a small, triangular depression left in wet clay by the angled tip of a stylus cut from a reed. The reed was held at an angle to the surface and pressed, not dragged. This is the distinction that matters most. Cuneiform was not drawn. It was pressed. The difference between drawing and pressing is the difference between a continuous gesture and a discrete one. A drawn line flows. A pressed mark stops. It is either there or it is not. This irreversibility was built into the medium. Once a mark was pressed into wet clay, it could not be erased without destroying the tablet's surface. Correction required a new tablet. Revision was not possible in the casual sense. Every mark was a commitment. The scribes who made them were not sketching or drafting. They were stating, in a medium that did not permit uncertainty, the precise sequence of impressions they intended to make. Precision was not optional. It was architectural. The basic vocabulary of cuneiform consists of 4 types of marks: a vertical wedge, pressed with the stylus held nearly perpendicular to the surface; a horizontal wedge, with the stylus nearly parallel; an oblique wedge, at an angle between the two; and a mark called the Winkelhaken, a German word meaning angle hook, which is made by pressing the corner of the stylus into the clay at a specific angle, producing a shape that looks something like a corner bracket. These 4 marks are all there is. From them, through combination and arrangement and positional variation, the entire cuneiform sign repertoire was built. Some signs required just 1 mark. Some required more than 20. But all of them, every number, every divine name, every royal proclamation ever pressed in cuneiform across 3,000 years of use, resolved at their most fundamental level to these 4 gestures. The structural economy of this is not immediately obvious, but it becomes so when you consider the alternative. Most ancient writing systems grew organically, accumulating marks from many sources, building irregular repertoires that reflected the accidents of their history rather than any underlying design principle. Cuneiform did the opposite. It converged. The earliest versions of the system were more pictographic, more varied, more organically complex. Over centuries, the signs were simplified and standardized until what remained was a system of remarkable formal economy, thousands of distinct signs, all built from 4 marks, all made by the same physical gesture in different orientations. One action. Infinite expression. A cuneiform sign does not mean one thing. This is the fact that takes longest to absorb and matters most once absorbed. In most modern writing systems, a letter or character has a primary function. It represents a sound, or a word, or a concept, and its meaning is relatively stable across contexts. In cuneiform, a sign is a node in a network. It can represent a word, or a syllable, or the first sound of a word used as a phonetic indicator, or a grammatical particle, or a conceptual category that modifies the word following it. Which function applies in any given context depends on the context. The reader of cuneiform was not decoding a cipher. They were navigating a system that assumed their intelligence. The layer of cuneiform that requires the most careful attention, because it is the most revealing, is the layer of what scholars call determinatives. A determinative is a sign that carries no phonetic value and is never spoken aloud. It exists for one purpose only, to indicate the semantic category of the word that follows it. There is a determinative for wooden objects. It precedes every word for a thing made of wood, telling the reader, before the word itself has been read, that what follows belongs to the category of wooden things. There is a determinative for bodies of water, one for gods, one for birds, one for stone objects, one for cities. These signs are structural. They are not part of the spoken text. They are labels embedded in the written form to organize the act of reading. The closest parallel in modern practice is not in literature or linguistics. It is in computer science. A determinative functions as a data type tag, a marker that specifies how the following token should be interpreted by the system reading it. In a programming language, a variable's data type tells the interpreter whether to treat a sequence of characters as a number, a string, a boolean, or something else. The determinative tells the cuneiform reader whether to interpret a sign as a wooden implement, a divine name, a geographic location, or a human being. The mechanism is structurally identical. One is made of clay. The other runs on silicon. The logic is the same. This parallel does not require any claim that ancient scribes were consciously doing what programmers do. The point is not intentional resemblance. The point is formal identity. The same logical problem, solved the same logical way, in two completely different contexts separated by 4,000 years. The problem is this: in any sufficiently complex information system, symbols become ambiguous. The same token can mean different things in different contexts. To resolve that ambiguity without requiring the reader to hold the entire system in working memory at all times, you need a mechanism for marking context before the ambiguous token appears. Determinatives are that mechanism. Data types are that mechanism. The solution was found twice, independently, because it is the only clean solution to the problem. The deeper implication of the determinative system is about how the Babylonians conceived of their world. A writing system that embeds semantic categories into its syntax is not merely representing reality, it is organizing it. The determinatives are a taxonomy. They divide the world into classes: wood, stone, water, divinity, humanity, and they require every written statement about any object to declare, first, which class it belongs to. The act of writing, in the cuneiform tradition, was simultaneously an act of classification. Information and structure were inseparable. This is not the behavior of a primitive notation system. This is a formal language. Beneath the symbolic signs and the silent determinatives, there is a third layer of the cuneiform system, one that operated according to entirely different rules and carried an entirely different kind of significance, the numerical layer. And it is here, in the way the Babylonians chose to represent quantity, that the first unmistakable shadow of modern computing logic appears. The most important fact about Babylonian numbers is not how many symbols they used, but how those symbols were arranged. The system was positional. In a positional number system, the value of a symbol is not fixed. It depends on where the letter sits relative to the others around it. The same mark, placed in different positions within a number, represents different values. This is so familiar to anyone who has learned modern arithmetic that it is almost impossible to see it as a design choice. But it is a design choice, and it is a profound one. Most ancient number systems were not positional. Egyptian hieroglyphic numbers, Roman numerals, Greek alphabetic numerals, all used different symbols for different magnitudes, requiring larger and larger repertoires of distinct marks as numbers grew larger. The Babylonian system sidestepped this problem entirely by encoding magnitude in position rather than in the symbol itself. The symbols themselves were minimal. To write any number, no matter how large, the Babylonian scribe needed exactly 2 marks, a vertical wedge representing 1 and a Winkelhaken representing 10. That is the complete set. 1 mark for ones, 1 mark for tens. Arranged in groups, repeated as needed, placed in positions that each carried a place value 60 times larger than the position to the right. This 2-symbol, positional system could represent any quantity from 0 to the astronomical. The intellectual compactness of this is remarkable. Everything from the price of a jar of oil to the distance of a planet could be expressed as the same 2 marks, in the same positional framework. Position value notation was not an accident or a convenience. It was a structural decision that made the Babylonian numerical system qualitatively different from what came before, and from what most of the ancient world developed independently. The decision to separate the meaning of a symbol from its identity, to make meaning a function of location rather than of form, is exactly the same decision that underlies every modern digital number system. In binary notation, the single symbol 1 can represent the number 1 in one position, 2 in another, 4 in another. The symbol itself does not change. The position changes. The Babylonian scribe and the microprocessor designer arrived at this principle from entirely different directions and through entirely different histories. They arrived at the same place. The number 60 was chosen as the base, meaning each positional column carries 60 times the value of the column to its right, for reasons that reward examination. 60 is the smallest number divisible by 2, 3, 4, 5, 6, 10, 12, 15, 20 and 30. No smaller number has this property. A base 60 system makes fractions of most common denominators exact rather than repeating. A property of immense practical value for a culture engaged in land measurement, astronomical observation, and the complex arithmetic of trade. The choice was not arbitrary, it was optimized. The Babylonians chose a base the way an engineer chooses a data format, by asking what kind of operations would be performed most often, and selecting the structure that made those operations cleanest. It is possible to admire the individual marks and miss the larger organization. To see cuneiform fully, you have to step back from the signs and the numbers and look at the tablet itself, not as a surface carrying text, but as an information object with a deliberate structure. Because Mesopotamian tablets, particularly the mathematical ones, were not written on randomly. They were formatted, they followed conventions, they had layouts. A typical mathematical tablet from the Old Babylonian period, roughly 2000 to 1600 BCE, divides its surface into distinct zones. The problem statement occupies one area, usually the upper portion or the left side. The procedure, the step-by-step working of the solution, occupies the central zone. The answer sits at the end, often separated from the procedure by a small horizontal line or a gap in the text. Some tablets carry a fourth zone, a verification. The answer is fed back into the original problem, and the result is checked against the known value. If the check passes, the tablet is complete. If it does not, but it always does, on the tablets that survive in finished form, the scribe would have started again. This spatial organization is not cosmetic. It reflects a conception of mathematical work as something with distinct phases: problem statement, procedure, result, verification. 4 phases, 4 zones. A complete computational cycle, recorded on a surface small enough to hold in one hand. The scribe who made this kind of tablet was not transcribing a calculation they had already done elsewhere. They were working through it on the tablet itself, following a structure they had been trained to follow, producing a record that was simultaneously a workbook and an archive, usable in the present, durable into the future. The most striking example of this organizational sophistication is a class of tablets that scholars describe carefully and rarely discuss at length in popular accounts. These are tablets that contain not one problem, but a sequence of related ones. A series of problems that share a common structure, but vary in one specific parameter. Problem 1. Given this initial value, apply this procedure. Problem 2. Given a slightly different initial value, apply the same procedure. Problem 3. Again, the same procedure, again a different starting value. The procedure never changes. Only the input changes. The set of problems covers the full range of valid inputs, systematically, one by one. In modern software engineering, this structure has a name. It is called a test suite. A test suite is a collection of controlled inputs and expected outputs used to verify that a procedure behaves correctly across the range of cases it is designed to handle. Every input is different. The procedure is constant. The outputs are checked. If any output fails to match the expected value, the procedure has a flaw. If all outputs match, the procedure is validated. The tablets that follow this pattern are not problems. They are validations. They are proof, pressed in clay, that the person who made them understood not just how to apply a procedure, but how to confirm that the procedure worked. These tablets were made before the Roman Empire, before the Greek city-states, before the alphabet that would eventually become this sentence. They were made by people whose names are almost entirely lost, who worked in buildings that have been rubble for 2,000 years, in a language that was already dead by the time Christ was born. And what they made, when examined without the comfortable assumption that the ancient world was primitive, looks less like an artifact of the past, and more like a blueprint for a future that was still 3,000 years away. Every time you check the time, you are using a number system designed in ancient Mesopotamia, not adapted from it, not loosely derived from it. The actual system, 60 seconds in a minute, 62 minutes in an hour, 360 degrees in a full circle, is the direct inheritance of a mathematical architecture built by Babylonian scholars sometime before 2000 BCE and never fully replaced in the 2 millennia since. This is not a trivial continuity. It is the signature of a design so well suited to its purpose that 40 centuries of mathematical progress have not found sufficient reason to discard it. The Babylonian choice of base 60 was not made casually. 6 is a highly composite number, divisible by more integers relative to its size than almost any other. 60 extends this property to a practical scale. A number system based on 60 can represent 1/2, 1/3, 1/4, 1/6, 1/10, 1/12, 1/15, 1/20, and 1/30 as exact values, no repeating fractions, no approximations, no remainders. By comparison, the decimal system we use today cannot represent 1/3 exactly. Try it. The threes go on forever. The Babylonians designed a system in which the divisions most commonly needed in practical calculation came out clean. This matters because a number system that produces clean fractions is a system that produces reliable intermediate results. In a long calculation, errors compound. If each step introduces a small approximation error, those errors multiply through the procedure and the final result drifts from the true answer. A system in which the common fractions are exact reduces this drift at every step. The Babylonian choice of base 60 was, in a precise technical sense, an optimization, a selection of numerical architecture on the basis of computational performance. It was the choice of people who calculated a great deal and cared about getting the right answer. The 360-degree circle follows from the same logic. 360 is divisible by 60, by 40, by 30, by 24, by 18, by 15, by 12, by 10, by 9, by 8, by 6, by 5, by 4, by 3, and by 2. A circle divided into 360 equal parts can be cleanly divided into almost any fraction that a geographer, astronomer, or engineer might need. This convenience was recognized by every mathematical tradition that encountered Babylonian astronomy, and they kept the degree. Every GPS coordinate in the world today is expressed in degrees, minutes, and seconds. Every navigational chart, every astronomical catalogue. The Babylonians made a choice about how to measure angles, and nobody since has found a compelling reason to change it. What this reveals about the Babylonian mathematical mind is not simply that they were clever. It reveals that they were systematic. They were not inventing tools for specific immediate needs and moving on. They were selecting foundations, mathematical architectures, on the basis of how those foundations would perform under a wide range of future applications. This is not the thinking of a culture that does arithmetic as an afterthought. This is the thinking of a culture that treats number systems as infrastructure, built to last, designed for generality, chosen with foresight. The architecture of their mathematics was, in the most precise sense, engineered. There is a number that most histories of mathematics treat as a late arrival, an invention of the Indian subcontinent in the 5th century of the Common Era, gradually transmitted westward through the Islamic world to reach Europe in the Middle Ages. That number is zero. The story of zero's invention is told as a story of a single transformative insight. The recognition that nothing, the absence of quantity, is itself a quantity, and can be represented by a symbol that allows arithmetic to be performed on it. This is a genuine and profound intellectual achievement, and the Indian mathematicians who formalized it deserve the credit they receive. What the standard history tends to omit is an earlier chapter in the same story. A chapter located not in India but in Babylon, not in the 5th century but some 7 centuries earlier, and not about zero as a number in the full mathematical sense, but about something that served the same architectural function in a positional system. Tablets from the Seleucid period, dating from roughly 300 BCE, carry a specific mark, a pair of diagonal wedges, used exclusively to indicate an empty positional column. Not a number, a placeholder. A marker that says, this column has no value, the next column over is what you need. To understand why this matters, consider how positional notation works without a placeholder. In the modern decimal system, the number 101 is written 101. The zero in the middle is not a number being added. It is a structural marker indicating that the tens column is empty. Without it, you cannot distinguish 101 from 11. The positional system requires a way to mark absence, or it becomes ambiguous in exactly the cases where ambiguity is most dangerous, when a value is present in a high position and absent in a lower one. The Babylonian placeholder solved this problem. It was not zero in the sense of a number that can be added or multiplied or treated as a quantity. It was zero in the sense of a structural marker for an empty position, a typographical device for making positional notation unambiguous. This distinction is real and important, but in computational terms, the distinction matters less than it might seem. A system that can represent absence explicitly, that has a symbol for the empty state in a positional column, is a system that can handle the full range of positional arithmetic without ambiguity. That system had been developed in Babylon's Cent Rishis before it appeared anywhere else. The question the narration is not yet ready to answer, but which it is worth asking, is why this fact does not appear in introductory histories of mathematics. The evidence has been available since the 1880s, when large numbers of Seleucid tablets were excavated and catalogued. The placeholder mark is plainly visible in photographs for those tablets. Scholars in the field have discussed it in technical literature for over a century. The gap is not in the evidence. The gap is between what specialists know and what general histories are prepared to say. That gap is itself a kind of information about what stories a culture finds comfortable and which ones it prefers to leave in the archive. Among all the mathematical tablets recovered from Mesopotamian sites, one category is so common, so consistent, and so straightforward in its purpose that it is easy to pass over it without registering its full significance. These are the table texts, systematic lists of pre-computed values arranged in ordered sequences, multiplication tables, reciprocal tables, tables of squares and square roots, tables of cube roots, tables of compound interest, laid out in neat columns on fired clay, row by row, the results already calculated and recorded, waiting to be consulted. The immediate explanation for these tables is practical efficiency. A Babylonian scribe engaged in a long calculation did not want to recompute standard products or reciprocals from scratch each time they were needed. The tables were reference resources, the ancient equivalent of a printed conversion chart or a physical slide rule. Consult the table, find the value, continue the calculation. This is how historians have typically described them, and this description is not wrong. The tables were certainly used this way, but the description undersells what was actually happening. When you separate the computation of a value from its application, when you compute all the products of, say, the number 16 in advance and record them permanently, so that any future calculation involving 16 can simply look up its needed product rather than recompute it, you are making an architectural decision. You are deciding that computation and application are separate activities, that it is more efficient to invest computational effort once in building a reference structure than to repeat that effort every time a value is needed. This decision is the foundation of one of the most important optimization strategies in modern computer science, the lookup table. In contemporary computing, lookup tables appear wherever the same computation must be performed repeatedly and the results can be pre-computed and stored. Graphics rendering engines use them for trigonometric functions. Cryptographic algorithms use them for substitution operations. Signal processing systems use them for filter coefficients. The reason is always the same. Computing from scratch takes time. Retrieving a stored result is fast. The trade-off between computation time and storage space is one of the central recurring problems in algorithm design, and the Babylonian table texts represent the earliest known systematic exploitation of the storage side of that trade-off. The Babylonian table of reciprocals is worth a closer look. Reciprocals, the result of dividing one by a number, were essential in Babylonian arithmetic because the system had no division operation in the modern sense. Division was performed by multiplying by the reciprocal. This meant that reciprocals were needed constantly, and the table of reciprocals was therefore not a luxury, but a computational necessity. But the table does not list all reciprocals. It lists only the reciprocals of numbers whose reciprocals have finite sexagesimal expressions. Numbers whose reciprocals repeat indefinitely in base 60 are absent. The table was curated, designed according to a formal criterion that determined what belonged in it and what did not. Someone thought about what a table of reciprocals was for, decided which values the table needed to contain to serve that purpose, and built it accordingly. The table is not a list of facts. It is an engineered information resource, built to specification. There is a useful exercise in reviewing what the previous sections have described. Not one feature at a time, but all at once, laid out next to each other, so that the pattern they form can become visible. Because each feature, examined individually, can be explained away as coincidence or clever practicality. Together, they are something else. The Babylonian writing system used marks that were discrete, each one either present or absent, with no gradation between. It organized those marks in positional sequences where meaning depended on location. It embedded categorical markers that specified how tokens should be interpreted. It recorded computations in structured formats with distinct zones for input, procedure, and output. It maintained pre-computed reference tables organized by formal selection criteria. It produced procedures designed to be replicated by anyone trained to use them. It included verification sequences that confirmed results by checking them against the original conditions. And it transmitted all of this through a formal educational infrastructure designed to produce specialists capable of applying the full toolkit. 5 architectural properties recur across these features. Discreteness. Every mark, every symbol, every value is binary in the sense of being either present or absent. There is no continuous gradient. There are only distinct states. Positional encoding. The value of every element depends on its location within a larger structure. The same mark means something different in different positions. Hierarchical layering. The system operates on multiple simultaneous registers, phonetic, logographic, numerical, categorical, each adding a different kind of information to the same surface. Formal procedure. Operations are defined by sequences of steps, each step specified unambiguously, the whole sequence terminating in a defined output. And systematic precomputation. Commonly needed results are computed once and stored for repeated retrieval, separating the act of computing from the act of applying. These 5 properties, taken together, are not a description of an ancient writing and arithmetic system. They are a description of an information processing architecture. They are the formal prerequisites for any system that reliably handles, stores, transforms, and retrieves structured information, regardless of what physical medium implements it. They appear in vacuum tubes, they appear in transistors, they appear in integrated circuits, they appear in the theoretical frameworks of Turing and Shannon and von Neumann, and they appear, fully present, in the clay tablets pressed in Mesopotamia 4,000 years before any of those names existed. The pattern does not prove that the Babylonians consciously designed a computing architecture. It does not prove that they understood what they were building, in the terms that a modern computer scientist would use. What it proves is something subtler and more interesting. That when a civilization dedicates serious intellectual effort to the problem of encoding, storing, and processing information reliably and efficiently, it converges on a set of architectural solutions that are not culturally relative. They are structurally necessary. The Babylonians did not invent these solutions, the way an individual inventor creates something new. They discovered them the way a mathematician discovers a theorem, by following the logic of the problem wherever it led, and arriving, as logic tends to arrive, at the only answers that actually work. The word binary gets used as a synonym for modern technology, as shorthand for computers, for digital systems, for the entire apparatus of the contemporary information age. This usage is not wrong, but it obscures what binary actually is. Binary is not a technology. It is not a notation. It is not an artifact of how computers happen to have been built. Binary is a logical principle, and it is one of the most fundamental principles in all of mathematics. Understanding it correctly is essential to understanding why it keeps appearing in places where it has no obvious right to be. The principle is this: information, any information, in any domain, can be represented using a system of discrete states, and the minimum number of states required to carry meaningful information is 2. One state carries no information. If everything is always in the same state, the state itself communicates nothing. 3 states carry more information than 2. But the additional complexity does not improve the fundamental architecture. It just adds a 3rd state that can be encoded as a combination of 2 binary positions anyway. 2 is the precise minimum. 2 is also, in the language of information theory, the natural base, the one to which the measure of information, the bit, directly corresponds. To see why 2 states are sufficient for any information at all, consider the simplest possible physical system. A light switch. A switch has 2 states, on and off. A single switch can encode a binary choice, yes or no, 1 or 0, this or that. A pair of switches can encode 4 distinct combinations, off-off, off-on, on-off, on-on. 4 combinations can represent 4 different messages. 3 switches can encode 8 combinations. 10 switches encode over 1,000. With enough binary switches, arranged in a positional sequence, where each switch's position carries a defined weight, you can represent any number, any letter, any image, any sound, any thought that can be expressed in structured form. 2 states, infinite reach. This is not a modern discovery. Gottfried Wilhelm Leibniz, the 17th century mathematician who formalized binary arithmetic in the West, understood it as a philosophical principle, a demonstration that the universe could be described using only unity and the void. He was not building computers. He was exploring the foundations of logic. The principle he described, though, was not new even in his time. Scholars of the I Ching had understood the combinatorial structure of binary sequences centuries earlier. And in the river valleys of ancient Mesopotamia, the same principle had been embedded in a numerical notation system so quietly, so practically, that no one thought to call it binary at all. It was just the way numbers were written. Ask what a binary system looks like when built from clay rather than transistors, from a reed stylus rather than a circuit board, and the answer is exactly what the previous chapters have been describing. A positional notation system using 2 types of marks, arranged in sequences where each position carries a weight, encoding any quantity through the combination and placement of those 2 marks. The hardware differs. The logic is identical. This is not an analogy or a loose comparison. It is a precise statement about the structural equivalence of 2 information encoding systems built in completely different contexts from completely different materials, by minds that had no knowledge of each other and no shared vocabulary for what they were doing. They were doing the same thing. The deepest version of the binary principle is not about technology at all. It is about the nature of information itself. Information exists as distinction, as the difference between one state and another. Where there is no distinction, there is no information. Where there is distinction, 2 states are enough to carry it. This means that any system capable of maintaining 2 distinct states, and of arranging those states in sequences, is capable of encoding any information that can be encoded at all. Clay tablets maintain 2 distinct states, mark and no mark. They can be arranged in sequences. The rest is mathematics. Lay a Babylonian mathematical tablet next to a description of binary notation, and the structural parallel emerges with a clarity that careful framing can neither manufacture nor obscure. The Babylonian numerical system used 2 marks, a vertical wedge representing 1 and a corner mark representing 10, arranged in positional sequences where each position carried a weight 60 times larger than the position to its right. The binary system uses 2 marks, 0 and 1, arranged in positional sequences where each position carries a weight 2 times larger than the position to its right. The base differs. The architecture is the same. The base difference is real and it matters, but it matters less than it might appear. The base of a positional system determines the size of the gap between adjacent positions, the multiplier applied to each column as you move leftward. It does not determine the fundamental structure of the system. A positional system using 2 marks in base 60 is positional, discrete, and 2 symbol in exactly the same sense as a positional system using 2 marks in base 2. The logical architecture, marks of fixed identity, positions of variable weight, values determined by the combination of identity and position, is identical. There is a natural objection to this parallel, and it deserves a direct answer. Isn't every positional number system essentially doing the same thing? Doesn't the decimal system also use position to determine value? The answer is yes, and this is exactly the point. The question is not whether positional systems share an architectural principle. They do. The question is how minimal the symbol set is. The decimal system uses 10 symbols. The Babylonian system used 2. These are architecturally different choices. A system with 10 symbols distributes information across symbol identity as well as position. A system with 2 symbols concentrates all the information in position and in the count of marks at each position. The information theoretic properties of the 2 approaches are distinct, and the 2-symbol approach is the one that maps directly onto binary encoding. The formal relationship between Babylonian sexagesimal notation and binary notation is not metaphorical, it is mechanical. A Babylonian number expressed in 2-mark notation can be converted to binary representation through a defined arithmetic procedure, the same kind of base conversion procedure that any student of computer science learns in the first weeks of study. The number 64 in Babylonian notation is a single corner mark in the 2nd position and 4 vertical wedges in the 1st. In binary, it is a 1 followed by 6 zeros. The path between these 2 representations is a sequence of defined arithmetic steps. Nothing is lost in translation. The information is identical. What changes in this framing is not the content of Babylonian mathematics, but the vocabulary available for describing it. The conventional vocabulary of ancient history describes the Babylonian numerical system as sophisticated, as positional, as remarkably advanced for its time. These descriptions are accurate. They are also incomplete. The complete description includes the fact that this system is, at the level of its information architecture, formally isomorphic to binary encoding. The same structure, the same properties, the same logical behavior, expressed in a different base and pressed into clay, rather than stored in semiconductor memory. The clay is 4,000 years old. The architecture has not aged at all. Return now to that small clay disc in the Yale Babylonian collection. The one with the square and the diagonal. The one with the number that does not fit the official story. The value inscribed on YBC 7289 is, in modern notation, 1.41421296. The true value of the square root of 2 to the same number of significant figures is 1.41421356. The difference between these 2 numbers is 0.00000060, 6 10/millionths. This is not an approximation in the casual sense of a rough guess or a rounded estimate. This is an approximation in the technical sense, the result of a convergent procedure that could in principle be continued indefinitely to produce any desired level of precision. The procedure was stopped at a point where the result was accurate enough for whatever purpose the maker had in mind. The stopping point was chosen. The precision was controlled. The procedure that produces this kind of result, an iterative, convergent approximation of a square root, is not difficult to describe. Begin with an initial estimate of the answer. Compute the average of that estimate and the number divided by the estimate. The average is a better approximation than the original estimate. Repeat the process using the better approximation as the new starting point. Continue until the result stabilizes to the desired precision. Each iteration roughly doubles the number of correct digits. Starting from a reasonable initial estimate, 6-figure accuracy requires only a few iterations. This procedure was named, in the 17th century, Newton's method, after Isaac Newton, who formalized a general version of this root-finding approach. It was later discovered that the method had been in use for centuries before Newton formalized it. in multiple mathematical traditions. It was renamed, in several textbooks, the Babylonian method, not as a gesture of historical generosity but as an accurate attribution. The iterative square root approximation procedure, documented on YBC 7289, is the earliest known record of an algorithm that modern numerical analysis would classify as a convergent root-finding method. The word algorithm is used deliberately here, not in the loose popular sense of any computerized process, but in the precise technical sense, a finite, unambiguous, step-by-step procedure that terminates in a defined output for any valid input. The Babylonian square root procedure is finite. It terminates when the approximation is close enough to the true value. It is unambiguous. Each step is defined clearly enough to be replicated by anyone following it. It terminates. It does not run forever. It is general. It works for any positive number, not just for 2. By every formal criterion, YBC 7289 is not a record of a specific calculation. It is evidence of an algorithm. The paradox in the tablet's name is not mathematical. It is cultural. An object in a university collection in New Haven, Connecticut, proves that a resident of ancient Babylon was implementing convergent iterative algorithms in clay some 3,700 years before the algorithm was named, formalized, and attributed to an English mathematician working in the 17th century. The algorithm has always been called the Babylonian method. The evidence that it originated in Babylon has been sitting in Yale's collection since 1909. The history books have not caught up. The mathematical tablets attract most of the attention when scholars discuss Babylonian intellectual achievement, and this is understandable. They are the most formally striking, the most directly comparable to modern mathematical practice. But the mathematical tradition was not the only domain in which the logical structures of computation appeared in ancient Mesopotamia. They appeared in the religious texts too, in the astronomical omens, in the medical diagnostic canons, in the legal codes. The logical architecture was not confined to one corner of the culture. It was the culture. The Babylonian omen texts form one of the largest bodies of cuneiform literature. The most important series, known as Enuma Anu Enlil, runs to some 70 tablets and contains thousands of individual entries, each recording the observed configuration of a celestial phenomenon and the consequence predicted to follow from it. The structure of these entries is consistent across the entire corpus and across the centuries during which the series was compiled and expanded. The template does not vary. If a particular condition is observed, then a particular outcome follows. If the condition is not observed, a different outcome applies. The logic is conditional and binary. A condition either obtains or it does not, and the response is determined accordingly. Conditional logic is the simplest and most fundamental form of computational decision-making. An if-then structure evaluates a condition, tests its truth value, and directs behavior based on the result. A decision tree organizes a hierarchy of such conditions, so that a complex question can be answered by traversing a branching sequence of binary choices. The Babylonian omen texts are, formally, decision trees. They encode a system for mapping observed inputs, celestial configurations, to predicted outputs, earthly consequences, through a branching structure of conditional statements. The tree is organized, curated, and applied systematically by trained specialists. It is not an informal body of accumulated wisdom. It is a structured information system. The medical diagnostic texts follow the same architecture. The diagnostic handbook, known in Akkadian as Sakiku, meaning all diseases, is a series of tablets organized around the same conditional template. If a patient shows a particular symptom or configuration of symptoms, then the diagnosis is this, and the prognosis is that. The if-then structure is explicit and consistent. The conditions are categorized by body part, by time of onset, by severity. The outcomes branch according to the conditions met. The handbook is not a collection of anecdotes. It is an expert system, a structured, traversable knowledge base, designed to support diagnostic decisions by specialists applying defined criteria to observed inputs. A civilization that organizes its religious practice as a set of conditional changes, its medical knowledge as a traversable decision tree, and its astronomical observation as an input-output mapping system is not accidentally doing computation. It has internalized the logical architecture of computation, the if-then structure, the binary truth value, the conditional branch, as a fundamental mode of thought expressed across every domain of structured knowledge it produces. The temples and the mathematical schools were separated by function. They were not separated by logic. The same architecture ran through both and through everything else. The word algorithm is one of those terms that has been borrowed so many times, stretched across so many different uses, and applied so loosely in everyday speech that its original precision has been almost entirely eroded. In popular usage, it refers to anything a computer does. The recommendation system that suggests your next video, the sorting function that arranges your email, the pricing model that adjusts an airline ticket 50 times a day. These are all algorithms in a real sense, but the casual usage obscures what makes an algorithm rather than simply a procedure or a rule of thumb. An algorithm, in its strict definition, has 4 properties. It is finite. It consists of a defined number of steps and terminates at a defined point. It is unambiguous. Each step is specified precisely enough that there is exactly one way to interpret and execute it. No judgment calls, no improvisation, no dependence on context not specified in the algorithm itself. It terminates. For any valid input, the process of following the steps will always reach an end. And it is general. It works not just for one specific input, but for any input within the class it is designed to handle. A procedure that lacks any of these 4 properties is not an algorithm. It may be a heuristic, a method, a practice, or a tradition. It is not an algorithm. This definition was not formalized until the 20th century, when mathematicians, including Alan Turing and Alonzo Church, developed the theoretical framework of computation. But the concept the definition describes did not originate in the 20th century, and neither did the objects that satisfy it. A finite, unambiguous, terminating, general procedure for transforming a class of inputs into a class of outputs is not a modern invention. It is a description of a structure that has been independently discovered and implemented multiple times across the history of human thought. The mathematical tablets of ancient Babylon implement this structure. They did not need a word for it. The tablets speak for themselves. The formal definition matters here because it is a filter. Applying it strictly to the Babylonian mathematical record separates genuine algorithms from procedures that merely resemble them. The claim this documentary is making is not that the Babylonians had something like algorithms, or that their mathematical methods were algorithm adjacent. The claim is that specific, identifiable tablets contain procedures that satisfy all 4 formal criteria: finite, unambiguous, terminating, general, and therefore qualify as algorithms in the strict, uncompromised sense of the word. This is a strong claim. It is supported by the evidence. And the evidence begins with a tablet that has been sitting at Columbia University for nearly a century. George Arthur Plimpton was an American publisher who collected ancient texts the way some people collect antiques, systematically, enthusiastically, and not always with perfect knowledge of what he was buying. In the early 1920s, he acquired from an antiquities dealer a small clay tablet from ancient Babylon, roughly the size of a paperback book's cover, broken at the left edge and carrying 4 columns of numbers in cuneiform. He donated it to Columbia University, where it sat in the Rare Book and Manuscript Library, catalogued as Plimpton 322, until scholars began to understand what it actually said. In 1945, the mathematician and historian of science Otto Neugebauer, working with Abraham Sachs, published a detailed analysis of the tablet's contents. Their finding was precise and surprising. The numbers on the tablet, when interpreted correctly, formed a table of Pythagorean triples, integer combinations of 3 numbers satisfying the relationship a squared plus b squared equals c squared. The tablet listed 15 such combinations, organized in descending order according to a specific mathematical parameter. The combinations were not random, not the result of trial and error, not a collection of examples accumulated over time. They followed a pattern that could only be explained by the application of a systematic generative procedure. The procedure in question, a parametric formula that generates Pythagorean triples by substituting pairs of regular numbers into a defined algebraic structure, is not stated on the tablet. The tablet shows only the outputs, but the pattern of the outputs makes the procedure mathematically recoverable, and recoverable uniquely. There is only one simple parametric formula consistent with the values in the table. The person who built the table applied a formula to a sequence of input pairs and recorded the results. They were not solving specific geometric problems. They were running an algorithm, a general procedure applied systematically across a defined range of inputs to produce a structured set of outputs. Plimpton 322 was made around 1800 BCE. The Pythagorean theorem is named for a Greek philosopher who lived around 570 BCE, roughly 12 centuries later. Standard account of mathematical history credits the Greeks with discovering the relationship between the sides of a right triangle. Plimpton 322 does not dispute that the Greeks formalized this relationship in the form of a proved theorem. It disputes the idea that the relationship was first known to the Greeks. The tablet demonstrates not just knowledge of the relationship, but systematic algorithmic exploitation of it. The generation of a structured table of Pythagorean triples using a parametric formula, organized by a mathematical ordering criterion. This is not a curiosity. It is evidence that the Greeks inherited, rather than originated, the mathematical foundation on which their geometry was built. The most recent and most sophisticated scholarly reading of Plimpton 322, proposed by Eleanor Robson in 2001, suggests that the tablet was a teaching resource created for the scribal schools. A worked example demonstrating to students how to apply the generative procedure to produce triples. This reinterpretation does not diminish the tablet's significance. If anything, it increases it. A tablet designed to teach an algorithm implies that the algorithm was institutionally recognized, formally taught, and considered part of the core curriculum of Babylonian mathematical education. The algorithm existed, it was taught, it was reproduced, it was applied. The standard history has not caught up. In the 7th century BCE, Babylonian astronomers accomplished something that should be impossible without a telescope, without calculus, without any of the formal mathematical apparatus that European scientists would develop 2,000 years later. They produced tables of lunar positions, accurate enough to predict eclipses decades in advance. Not roughly, not approximately. With a precision that modern astronomers, checking the Babylonian predictions against modern ephemeris calculations, have verified as genuinely impressive. Within the constraints of what the naked eye can observe and what clay tablets can record. They did not do this by watching the sky more carefully than anyone else, though they did watch it carefully. They did not do it through inspired geometric insight, though they understood the geometry of celestial motion. They did it by building mathematical models, structured, sequential, arithmetic procedures that took a known celestial state as input and produced a predicted future state as output. The models were computational. The computation was performed not by machines but by human specialists, applying defined arithmetic procedures to tabulated values. Step by step, tablet by tablet, generation by generation. The two major Babylonian computational frameworks for astronomical prediction are known to modern scholars as System A and System B. System A models the varying speed of the Moon, which moves faster when closer to Earth and slower when farther away. Using a step function, the sky is divided into two zones, and the Moon's daily motion in each zone is a fixed, defined value. When the Moon crosses from one zone to the other, its daily motion changes to the other fixed value. This is not physically accurate. The Moon's actual motion varies continuously, not in steps, but it is computationally tractable. The step function captures the essential feature of the phenomenon, the variation in speed, in a form that can be calculated systematically and extended indefinitely forward in time. System B uses a different approximation, a linear zigzag function, in which the Moon's velocity increases by a fixed amount each day until it reaches a maximum, then decreases by the same fixed amount until it reaches a minimum, then increases again. The velocity traces a regular sawtooth pattern. This is also not physically exact, but it is a better approximation than a step function for some purposes, and it is equally tractable computationally. Given the initial state, the Moon's velocity at a known date, the entire future sequence of velocities can be computed by repeated addition or subtraction of the fixed increment. The procedure is a loop. Apply the increment, check against the maximum or minimum, reverse direction if needed, repeat. Both systems are, in the precise technical language of numerical computing, discretized dynamic models. They replace a continuous physical process with a sequence of discrete computational steps that approximate the process's behavior over time. This is what computational simulations do. This is what numerical integration does. This is what every physical model implemented on a digital computer does. Replace the continuous differential equations of physics with discrete arithmetic steps that can be executed sequentially. The Babylonian astronomers were doing numerical simulation in clay, with arithmetic rather than differential equations, because differential equations had not yet been invented. The computational architecture was identical. The mathematical vocabulary was not. There is a structure that appears in Babylonian mathematical tablets across every domain where those tablets survive in significant numbers. It appears in the astronomical computation tables, where the same arithmetic operation is applied day after day to produce a running sequence of celestial positions. It appears in the square root calculations, where the same refinement procedure is applied repeatedly to an improving approximation. It appears in the labor allocation tablets, where the same formula for worker productivity is applied to a series of different project scales. It appears in the land measurement texts, where the same procedure for computing area is applied to a sequence of different plot dimensions. The structure is a loop. An initial value is established. An operation is applied to it. The result becomes the new starting value. The operation is applied again. This continues until a stopping condition is met. A desired precision is reached, a sequence is complete, a target value is achieved. The operation within the loop may be simple arithmetic, or it may be a complex multi-step procedure. The loop itself is the same in every case. Define a state, transform the state, check a condition, repeat if the condition is not yet satisfied. The loop is so fundamental to computation that it is sometimes treated as a synonym for it. The power of the loop is that it converts finite capability into effectively unlimited processing. A procedure that can be applied once to one input can, through looping, be applied any number of times to an evolving state. The same steps, the same rules, iterated across time or across a sequence of inputs, produces results of arbitrary complexity and precision from operations of finite simplicity. This is what gives computation its apparent power beyond its apparent means. It is also what gives Babylonian mathematics its apparent precision beyond its apparent tools. The labor allocation tablets offer a particularly clear window into the Babylonian use of iteration. These are tablets that address problems of the form: a task requires a defined amount of work, workers of a defined productivity are available, how many workers are needed for how many days. The answer involves multiplication and division, but the tablet does not merely record the answer for one specific task. It applies the same procedure to a structured sequence of related problems, varying the task sizes, or the productivity rate, or the time available, and records the answer for each. The procedure is the constant. The input is what varies. The output is a table of results that allows decisions to be made across a range of scenarios without any further computation. This is what computational power actually looks like when you separate it from its modern technological trappings. It is not speed, it is not scale. It is the recognition that a procedure applied consistently to varying inputs produces structured outputs that carry more value than any single computation. The Babylonians understood this principle and embedded it in their mathematical practice so thoroughly that it appears not as an innovation or an exception, but as the normal, expected way of working with quantitative problems. The loop was not a clever trick, it was the default. There is a Sumerian text, modest in length and remarkable in detail, that describes a single day in the life of a student scribe. The text is more than 4,000 years old. It is known to scholars as the school day's tablet, or sometimes simply as a school day, and it reads with a specificity that suggests it was written not as fiction, but as a faithful account of a real institution and a real daily experience. The institution was the Idubba. The Sumerian phrase means tablet house, and the daily experience was one of the most rigorous intellectual curricula in the ancient world. The student in the text wakes before dawn. He eats quickly, packs his prepared clay tablets, and goes to the tablet house. He is late. The teacher notes his lateness. He sits at his assigned place. The tablet house had assigned places, structured seating, a physical organization that reflected the hierarchy of learning levels within it, and begins his work for the day. The work is copying. He copies a model text onto his tablet, pressing each mark in sequence, each wedge at the correct angle, each sign in the correct form. The teacher walks behind him and corrects the marks that are wrong. At the end of the day, the student smooths his tablets for reuse. The next day is the same. This was not the whole curriculum. The daily copying built hand skills and sign recognition, but the Adaba also taught mathematics in a structured, sequential program. The students began with arithmetic, basic operations, standard tables, the multiplication and reciprocal tables they would use throughout their careers. They progressed to geometry, area calculations, volume formulas, the properties of standard shapes. They moved on to algebraic procedures, learning to solve quadratic and cubic equations, using techniques that European mathematicians would not rediscover until the Renaissance. The most advanced students learned astronomical calculation, the procedures for predicting celestial events that required fluency with the full toolkit of Babylonian computational method. The curriculum took years. The skills it produced were not common. A trained scribe emerging from the Adaba was not a clerk in the modern sense of someone who records what others decide. They were a specialist, someone whose training gave them access to a body of technical knowledge that most of the population had no contact with, and whose professional function was to apply that knowledge in service of the administrative, commercial, and astronomical needs of the institutions they worked for. The temples, the royal courts, the large trading houses. These institutions ran on the output of scribal expertise. The scribes were the operational layer of Babylonian civilization. The Adaba was not simply a school in the sense of a place where knowledge is transmitted. It was a research and production institution, a place where existing knowledge was copied, studied, extended, and applied, and where the next generation of specialists was trained to continue the work. The tablets produced in the Adaba were not exercises to be discarded. They were added to the institutional archive. New problems were developed and solved. New tables were compiled. The body of knowledge grew, tablet by tablet, generation by generation, inside an institution specifically designed to make that growth possible. The computational tradition of Mesopotamia was not an accident. It was the output of an institution whose entire purpose was to produce and maintain it. Not everything that was known was shared. This is a feature of knowledge in every culture and every era, but in Babylonian scribal practice, it takes a particular and telling form. Certain tablets carry, at their end, explicit written instructions about who may and may not read the contents. These instructions are not vague. They are not rhetorical. They are direct, practical, and specific. The knowledgeable should not show this to the unknowledgeable. This is a secret of the great gods. Do not let it pass to anyone who does not know it. The categories of knowledge, most frequently marked with these restrictions, are revealing. Advanced astronomical calculation methods, particularly the procedures for predicting eclipses, appear under access controls with notable frequency. Medical diagnostic procedures of the highest complexity, those involving the interpretation of subtle symptoms or the management of serious conditions, are sometimes similarly restricted. Certain classes of mathematical technique associated with divination appear under secrecy instructions. The common thread is not mysticism. The common thread is operational power. The ability to predict an eclipse was not merely a scientific achievement in ancient Mesopotamia. It was a political instrument. Eclipses were interpreted as omens of exceptional gravity, portents of the death of kings, the fall of dynasties, the outcomes of military campaigns. A court astronomer who could announce, weeks or months in advance, that an eclipse would occur on a particular night held influence that went well beyond scientific prestige. They could advise the king to prepare countermeasures. They could announce divine warnings. They could shape royal decisions. The predictive algorithm embedded in the astronomical tablets was, in the most direct sense, a tool of power, and like all tools of power, it was protected. The modern parallel is exact, and the fact that it is exact is more interesting than the parallel itself. Technology companies restrict access to their core algorithms, not because those algorithms are mysterious, but because they are valuable. The access control is not spiritual, it is strategic. The organization that controls a powerful information processing method controls the outputs of that method, and those outputs translate into advantage, commercial, military, or political. The Babylonian scribes who inscribed access restrictions onto their tablets were not performing a ritual of secrecy. They were practicing information security. They understood, with clarity, that a computational method is a form of leverage, and they managed that leverage accordingly. What the access control colophons reveal is a culture that had arrived at a sophisticated understanding of the relationship between knowledge and power, not as an abstract philosophical principle, but as a practical reality that required practical management. The technical knowledge was not distributed democratically. It was held by specialists, produced in dedicated institutions, applied through professional hierarchies, and explicitly protected from unauthorized access. This is not the organization of a primitive civilization feeling its way toward written culture. This is the organization of a society that had been running on formalized, protected, institutionalized technical knowledge for long enough to develop explicit protocols for managing it. At the end of a formally produced Babylonian tablet, after the text was complete and the content had been pressed into the clay, the scribe added a final section. This section was not part of the text itself. It was about the text, a structured annotation recording the provenance, the authorship, the date, and the accuracy of what had just been written. Scholars call this the colophon, from the Greek word for finishing touch. In the Babylonian tradition, it was not optional. For any tablet intended as a permanent record or an archival resource, the colophon was as necessary as the content it followed. A typical colophon recorded the name of the scribe who had produced the tablet. It recorded the name of the institution or individual the tablet belonged to. It recorded the date, in the regnal year of the ruling king, and the month and day of the Babylonian calendar. It recorded the source text, the earlier tablet from which this one had been copied, so that the chain of transmission could be traced. And it often carried a specific statement about the accuracy of the copy, checked and verified against its original, or copied from an old tablet and restored where damaged. The colophon was a formal assertion of intellectual provenance. The function of this system becomes clear when you consider what it made possible. Any tablet in a well-maintained Babylonian archive could be traced backward through its colophon to the tablet it had been copied from, and that tablet's colophon could be traced to an early original, and so on back through successive generations of mapping to whatever the oldest surviving of the text was. The chain of custody was, in principle, complete and verifiable, not because any central authority enforced it, but because the convention of recording provenance was embedded in professional practice deeply enough that it was observed consistently across institutions and across centuries. In contemporary software development, this function is performed by version control systems. A version control system records every change to a piece of code, annotated with the identity of the person who made the change, the time at which it was made, and a description of what was changed and why. It maintains a complete history of the code's development, making it possible to trace any current version back through every previous version to the original. Code can be compared across versions, errors can be traced to their origin, and changes can be attributed precisely. The colophon does all of these things for clay tablets. The vocabulary is different. The function is identical. The most striking single example is a tablet from Ashurbanipal's library at Nineveh, carrying a colophon that reads, in the careful translation of scholars who have spent careers working with such texts, copied from an older tablet, checked against it, not a single sign altered. The scribe had compared their fresh copy to a verified original, mark by mark, and certified the result. They had, in the language that a modern software engineer would immediately recognize, performed a diff, a systematic comparison of two versions of a text, to confirm that no unintended changes had been introduced. The comparison was recorded. The certification was part of the permanent record. The Babylonians did not invent version control as a metaphor. They practiced it as a profession. Ashurbanipal, the last great king of the Assyrian Empire, understood something that few rulers before or since have understood with equal clarity. The durability of an empire is not a function of its military power. Armies dissolve, borders shift, cities are sacked and rebuilt and sacked again. What outlasts all of these things, if it is properly maintained, is knowledge, systematically collected, carefully organized, and preserved in a form that can survive the ordinary catastrophes of political history. Whether Ashurbanipal arrived at this insight through philosophical reflection or practical calculation is impossible to know. What is known is that he acted on it with the thoroughness of a man who takes his conclusions seriously. Across the later decades of his reign, which lasted from approximately 668 to 627 BCE, Ashurbanipal dispatched scholars to every significant archive and temple library in his empire, with standing orders to copy any text of importance and send the copies to Nineveh. He did not wait for texts to come to him. He reached out to collect them. Correspondence that has survived from this period shows the king writing personally to provincial administrators and temple authorities, requesting specific texts, following up when copies were slow to arrive, specifying that he wanted originals when copies were insufficient. He knew which texts he wanted. He knew who had them. He pursued them systematically. The result, assembled in the royal palace at Nineveh in what is now northern Iraq, was a library estimated by scholars to have held between 25,000 and 100,000 tablets. The range reflects uncertainty about what was lost before proper archaeological study began, not uncertainty about whether the library was extraordinary. The collection was organized. Tablets were grouped by subject and series. Finding catalogues were produced. Clay tablets whose content was a listing of other tablets, organized to allow a reader to locate a specific text within the collection. The organization was not informal. It was systematic, maintained by professional staff, and designed for active use rather than mere storage. The library contained everything: literary works, including what we now call the Epic of Gilgamesh, the oldest surviving work of narrative literature, medical diagnostic texts, mathematical tablets, astronomical observation records and prediction tables, omen series of every kind, legal codes, religious hymns and ritual instructions, administrative records, historical chronicles. The scope was not accidental. Ashurbanipal was not a passive collector accepting whatever came his way. He was pursuing comprehensiveness deliberately, assembling what he apparently conceived of as a complete record of the knowledge of his civilization. Whether he achieved that goal is impossible to say. The library he built was the largest organized collection of knowledge the ancient world had yet produced. In 612 BCE, a coalition army of Babylonians, Medes and Scythians besieged Nineveh. The city fell after 3 months. The palace was sacked, then burned. The Assyrian Empire, which had dominated the Near East for centuries, ceased to exist within a decade. The historical record of what happened inside the palace during those final days is fragmentary, but the archaeological record, excavated slowly and incompletely since the mid-19th century, tells its own story. The story has an unexpected twist. Clay tablets do not burn, they bake. The fire that destroyed the palace at Nineveh transformed the unfired clay tablets, those that had been kept soft for active use rather than hardened for archival storage, into permanently preserved objects. The very disaster that ended the Assyrian Empire preserved a significant fraction of Ashurbanipal's library in a form more durable than the scholars who assembled it could have achieved deliberately. The fire was the most effective preservation event in the library's history. But preservation is not the same as survival. Thousands of tablets shattered in the collapse of burning roofs and falling walls. Thousands more were scattered during the sack of the city and carried off as plunder or simply abandoned in the rubble. Later excavations, conducted in the 19th century by workers with little archaeological training, under time pressure, without systematic recording, removed enormous quantities of tablets without preserving the contextual information that would have made them fully interpretable. The texts survived. The record of where they were found, how they were organized, what surrounded them, did not. The catalogue tablets, the finding aids that recorded what was in the library and where each text was located, are particularly painful in their implications. These tablets list the first lines of texts, their series numbers, their locations within the collection. When scholars compare these catalogue entries to the tablets that have been physically recovered and translated, the gaps are visible and specific. Entire series of text appear in the catalogue and nowhere in the physical collection. The catalogue entry describes a text. The text itself is gone. The library's own finding system has become a monument to what was lost, a detailed inventory of an absence, pressed in clay that survived when everything it pointed to did not. The broader pattern of loss across the Mesopotamian archaeological record compounds the problem. The sites of Nippur, Babylon, Uruk, and dozens of smaller cities have been excavated at various times, and with varying degrees of care over the past century and a half. What survives from these excavations is not a representative sample of the tablets that existed. It is a heavily filtered subset, shaped by which buildings collapsed in ways that preserved their contents, which areas were excavated with sufficient care to recover small objects, and which tablets were hard enough to survive handling by 19th century workmen, with baskets and donkeys rather than trowels and brushes. The algorithmic knowledge documented in the surviving corpus is not the ceiling of what existed. It is whatever the floor happened to hold. The tablets that survive do not survive because they were the most important. They survive because of accident, the particular geometry of how a roof collapsed, the specific temperature reached in a fire, the decision of an excavator to dig in one spot rather than another. Understanding this contingency is essential to reading the surviving record correctly. What we have is not a curated selection of the best or most significant texts. It is a random sample, biased in specific ways by the physics of preservation and the sociology of archaeology. Some tablets survived because they were buried deliberately. In ancient Mesopotamia, it was common practice to deposit objects beneath the foundations of important buildings as dedicatory offerings, a practice intended to preserve a record of the building's construction for any future ruler who might rebuild or renovate the site. These foundation deposits sometimes included tablets recording the identity of the original builder and the nature of the building. Buried in stone boxes, insulated from the physical damage that afflicted above-ground archives, these tablets survived the entire lifespan of the buildings above them and waited for archaeologists in a state of near-perfect preservation. Other tablets survived through the accidents of flooding, abandonment, or deliberate concealment. Wells and cisterns that were closed and forgotten sometimes preserved the tablets that fell or were thrown into them. Rooms that were abandoned intact and sealed by the collapse of their roofs sometimes preserved their contents in the compressed, intact state that archaeologists find most informative. The Sippar Temple Library, excavated by Hormuzd Rassam in 1882, was one of these. The tablets had been stacked on wooden shelves. The wood had long since decomposed, but the tablets had settled into neat, layered piles on the floor that preserved the organization of the shelves. And the organization, carefully documented by Rassam's team, revealed how an ancient archive had actually been arranged. The geographic distribution of surviving mathematical and astronomical tablets is not random. The major concentrations appear at Nippur, Sippar, and Uruk, cities that were not primarily administrative or commercial centers, but centers of scribal and intellectual activity. Nippur in particular, which served as the religious center of Sumer and later of Babylonia, has yielded enormous quantities of mathematical tablets, including many of the most significant examples used in this documentary. The concentration at Nippur is not accidental. It reflects the fact that mathematical education and practice were concentrated in the institutional networks associated with the major temples, and the major temples were in cities like Nippur. What this geography of survival implies about the record is both encouraging and humbling. It is encouraging because the tablets that have been found and studied were produced by the institutions most central to the Babylonian computational tradition. The scribal schools associated with the great temples where the most sophisticated mathematical work was done. The sample we have is biased toward the best, not toward the average. It is humbling because even this best-case sample represents, by any reasonable estimate, a tiny fraction of what was produced. The Sippar Archive, one of the largest and best-preserved deposits of mathematical tablets ever found, almost certainly represents one institution's collection over one period of its history. Across the full span of Mesopotamian civilization, across all its institutions and all its centuries, the scale of what was produced and what is gone is beyond precise estimation. There is a number that changes the frame of this entire documentary. It is an estimate, not a precise count, but it is grounded in institutional surveys, ongoing excavation reports, and the documented holdings of the major repositories. The number is this: there are approximately 500,000 cuneiform tablets currently in the possession of museums, universities, national collections, and private holders around the world. 500,000 objects, each one carrying text pressed in clay by someone whose world was already ancient when Rome was young, and the majority of them have never been translated. The British Museum holds approximately 130,000 cuneiform tablets. Of those, a significant portion has been catalogued but not translated, described by acquisition date, physical condition and approximate content category, but never fully read. The Vorderasiatisches Museum in Berlin holds tens of thousands more, the Louvre in Paris, the Oriental Institute in Chicago, the Yale Babylonian Collection, the Iraq Museum in Baghdad, whose holdings were severely damaged in 2003 and whose full extent remains uncertain. American and European universities hold additional thousands, some acquired in the 19th century, some more recently, many sitting in storage rooms that have not been systematically reviewed in decades. The implications for what this documentary has been arguing are uncomfortable in both directions. On one hand, the extraordinary mathematical and computational knowledge documented on the translated tablets was found in a fraction of the total record. The 5-figure approximation of the square root of 2, the parametric algorithm for Pythagorean triples, the iterative astronomical models, the conditional logic of the omen texts. All of this came from a sample that represents, at generous estimate, perhaps 5 to 10% of the surviving tablets, and a far smaller fraction of what was originally produced. The algorithmic knowledge documented in that sample is already remarkable. What remains in the untranslated portion is genuinely unknown. On the other hand, this same fact disciplines the documentary's claims. The evidence presented here is real, specific, and supported by scholarly work spanning more than a century. It is not the full record. It is the accessible corner of a record whose full extent remains unread. The claims are strong, formally, demonstrably strong, but they are claims made from a partial dataset. The conclusion of this documentary is not that the Babylonians invented computing in the full modern sense. The conclusion is that the intellectual foundations of modern computing were present in the Babylonian mathematical tradition 4,000 years before computing as such existed, and that this conclusion rests on a fraction of the available evidence. What the full evidence will say, when the 500,000 unread tablets are eventually processed, is a question that belongs to the future. Otto Neugebauer was born in Innsbruck in 1899, trained as a mathematician in Munich and Göttingen, and spent the 1930s in Copenhagen before the political situation in Europe compelled him to emigrate to the United States, where he eventually settled at Brown University and spent the rest of his career. None of this biographical detail is particularly dramatic, but what Neugebauer did with the decades of his working life constitutes one of the most significant intellectual revisions of the 20th century. A revision that reshaped what scholars understood about the history of mathematics, and that the broader culture has, with remarkable consistency, declined to absorb. Neugebauer came to the study of ancient mathematics as a practicing mathematician, someone trained to read mathematical texts not as historical documents, but as mathematical arguments, to follow the procedures they described not merely to understand their context, but to evaluate their content. When he turned to the Babylonian mathematical tablets in the 1930s, he brought this mathematical literacy to a corpus that previous scholars had approached primarily as philological objects, texts to be translated, not procedures to be understood. The difference in approach produced a difference in findings that was nothing short of revolutionary. What Neugebauer found, and what he published in meticulous technical detail across a series of works in the 1930s and 1940s, was that the Babylonian mathematical tradition was not primitive, not limited to basic arithmetic, and not confined to practical commercial calculation. The tablets contained quadratic equations solved by completing the square, a procedure that European algebra textbooks attributed to the 9th century Islamic mathematician Al-Khwarizmi. They contained systems of linear equations solved by elimination. They contained methods for computing cube roots and fourth roots. They contained what appeared to be the foundations of trigonometric calculation. The mathematics was not merely ahead of what scholars had previously attributed to the ancient Near East. It was ahead of what had been attributed in the standard history of mathematics, to the Greek tradition that supposedly gave birth to the mathematical tradition of the Western world. The implications of Neugebauer's findings were direct and disturbing. If the Babylonians had solved quadratic equations by completing the square 1,000 years before the Greeks, and if Pythagoras had spent time in Babylon, and if the Greek mathematical tradition showed precisely the kinds of results that would follow from access to the Babylonian foundations, then the story of Greek mathematical genius, inventing rigor and proof and abstract mathematics from essentially nothing, was not accurate. It was a story that required substantial revision at its foundations. Neugebauer documented this in extraordinary detail. He published it in German and in English. He taught it to generations of students at Brown. And the standard history of mathematics, as taught in schools and described in popular accounts, did not change. The gap between specialist knowledge and popular narrative is a familiar feature of academic culture, but in this case the gap is unusually wide and unusually long-standing. Neugebauer's core findings have been confirmed, refined, and extended by every subsequent generation of scholars working in the field. There is no serious dispute among specialists about the mathematical sophistication of the Babylonian corpus. The dispute is entirely in the popular historical narrative, where the Greeks remain, as they have been for centuries, the founding geniuses of mathematics, a story that Neugebauer's work showed to be at best significantly incomplete. In 2001, a British scholar of ancient mathematics named Eleanor Robson published a paper in the journal Historia Mathematica that attracted more public attention than most academic papers in the history of mathematics have ever received. The paper was titled Neither Sherlock Holmes Nor Babylon, a reassessment of Plimpton 322. Its argument challenged the standard interpretation of the most famous Babylonian mathematical tablet, and when news coverage summarized its conclusions, the story was typically presented as a debunking, as evidence that the computational sophistication scholars had attributed to ancient Babylon had been overstated. The coverage was wrong, but it was wrong in an instructive way. Robson's argument was not that Plimpton 322 is less mathematically sophisticated than Neugebauer had claimed. Her argument was that the standard interpretation of what the tablet was for, the interpretation that framed it as a reference table for calculating angles in right triangles, possibly used by surveyors or architects, was anachronistic. It imposed modern mathematical categories and use cases onto an ancient object without sufficient consideration of the context in which the object was produced. When Robson analysed the tablet in the context of the scribal school curriculum, the institutional setting in which it was most likely made, a different picture emerged. The numbers on Plimpton 322, Robson argued, are best understood as the output of a teaching procedure, a worked example designed to show students of the Adaba how to apply a specific numerical method to generate pairs of numbers with particular properties. The tablet was a pedagogical resource, not a practical reference tool. This reframing changes the cultural meaning of the tablet. It does not change the mathematics. The procedure used to generate the tablet's contents is the same in both interpretations. A parametric formula applied systematically to a sequence of inputs, producing a structured set of outputs. The algorithm is the same. Only its institutional purpose changes. And in one important respect, Robson's reinterpretation strengthens rather than weakens the computational reading of the tablet. A practical reference table for working surveyors is impressive evidence that a mathematical method existed. A pedagogical resource designed to teach students how to apply a mathematical method is evidence of something more. It implies that the method was not just used but taught, that it was considered part of the core competence of a trained specialist, institutionally recognized, formally transmitted, and reproduced across generations of scribal students. A method that is taught to every advanced student in an educational institution is not a clever trick found by one brilliant individual. It is a foundational piece of a computational tradition. The popular coverage of Robson's paper missed this distinction entirely. Debunking makes a better story than nuance, and the headline version, Babylonian mathematical sophistication overstated, was easier to transmit than the accurate version. Babylonian mathematical sophistication differently contextualized, and thereby more significant. What Robson had actually done was show that the algorithmic thinking documented in Plimpton 322 was not an isolated achievement. It was curriculum. It was the expected competence of a trained professional. It was what the Aduba was built to produce. The tablet does not represent a peak of Babylonian mathematical knowledge. It represents the floor, the level of algorithmic capability that every serious student was expected to master. The ceiling is somewhere else, in tablets not yet found or not yet read. The most recent development in the study of Babylonian mathematical knowledge is not an archaeological discovery or a scholarly reinterpretation. It is a technological one. And it is, in the context of this documentary, impossible not to notice the symmetry. The intellectual tradition that gave rise to algorithmic computation is now being studied by algorithmic computation. The tools of the present are reading the archive of the distant past. The loop, as it turns out, is very long. In 2023, a collaboration between computer scientists and Assyriologists produced a machine learning model trained to read and interpret damaged cuneiform inscriptions from digital photographs of tablets. The model was built using the corpus of translated tablets as training data. Thousands of photographs paired with scholarly transcriptions, used to teach the system to recognize cuneiform signs in varying states of preservation, under different lighting conditions, and with different degrees of surface damage. The result was a system capable of suggesting reconstructions of missing or damaged text, with an accuracy that surprised specialists who tested it against tablets with known correct readings. The challenge this addresses is not a small one. Reading cuneiform at the level required for mathematical and astronomical tablets is a skill that takes years to acquire, and there are perhaps a few hundred specialists worldwide capable of doing it at the level required for the most technically complex material. Against a backlog of hundreds of thousands of untranslated tablets, the capacity of the human specialist community is simply insufficient to work through the record in any reasonable time frame. Without assistance, the 500,000 unread tablets will remain substantially unread for generations. With AI assistance, with systems capable of handling routine signs and suggesting readings for damaged passages, allowing human specialists to concentrate their attention on interpretation rather than transcription, the timeline changes dramatically. The implications for what this documentary has argued are direct. The evidence for algorithmic thinking in ancient Babylon, the iterative procedures, the parametric table generation, the positional encoding, the test suites, the conditional logic, was found in a fraction of the available corpus. That fraction was the accessible one, the tablets translated through human scholarship over a century and a half of patient, specialized work. The rest of the corpus, the tablets in storage drawers, in uncatalogued collections, in institution basements around the world, remains unread. What it contains is not known. The AI systems now being developed and deployed in Assyriology are not yet capable of independent scholarship. They are tools for acceleration, for extending the reach of human expertise rather than replacing it. But they are already finding things that human readers missed: subtle patterns in sign distributions, anomalous numerical sequences, structural regularities that become visible only when large amounts of text can be processed quickly. The question of what the full Babylonian corpus will reveal, when it has been read in its entirety, is not a question that can yet be answered. It is a question that the machines and the scholars are, together, beginning to ask. Greek mathematics appears in the historical record suddenly and at a level of sophistication that demands explanation. In the 6th century BCE, the philosophical tradition associated with Thales of Miletus begins to produce results. The prediction of eclipses, the geometric theorems attributed to Thales himself, that imply access to mathematical knowledge considerably beyond what any purely indigenous Greek tradition could have developed in the time available. By the 5th century BCE, Pythagoras and his school are working with results about number theory and geometric relationships that mirror, in their content and their method, the Babylonian mathematical tradition this documentary has been describing. By the 4th century, Eudoxus is developing a theory of proportion that resolves exactly the mathematical problems that the Babylonian irrational approximation procedures had addressed by a different means. The accumulation of content is too specific to be independent invention. The question of how Greek mathematics relates to the Babylonian tradition it follows is one of the most carefully avoided topics in the standard history of science. The avoidance is not always explicit. It appears more often as an absence, as the failure to ask a question that the evidence makes obvious. Where did Thales learn to predict eclipses? The Babylonian astronomical tradition had been producing eclipse predictions for centuries before Thales. Thales is known to have travelled to Egypt, and the Egyptian mathematical tradition was in contact with the Babylonian one. The route from Babylon to Thales is not difficult to trace in general terms. The specific mechanism of transmission is simply never examined in the accounts that celebrate Thales as the father of rational inquiry. The case of Pythagoras is more direct. Multiple ancient sources record that Pythagoras travelled extensively before establishing his school in Croton, to Egypt, to Babylon, and possibly to other centres of ancient learning. The figure of 12 years in Babylon, which appears in some accounts, may be exaggerated or legendary, but the claim of Babylonian contact appears too consistently and in too many sources to be entirely dismissed. And the content of Pythagorean mathematics, the theorem that bears his name, the study of number ratios, the interest in the mathematical properties of musical intervals, maps with suspicious precision onto the material that Babylonian scribal students were learning in the Idubba 1,000 years earlier. The theorem was being applied algorithmically in Babylon before Pythagoras was born. Pythagoras was in Babylon. The connection the official history declines to draw is not a fringe inference. It is the simplest explanation available. The resistance to drawing this connection is not irrational. It is in part the appropriate caution of scholars who understand that transmission requires specific, documented evidence rather than plausible inference. In part, it reflects the genuine difficulty of establishing exactly how knowledge travelled in a world, without printing, without academic journals, without the institutional infrastructure for knowledge transmission that we now take for granted. And in part, it reflects the weight of a historiographical tradition in which Greek intellectual achievement has been framed, for centuries, as a unique origin point rather than a synthesis of inherited elements. That framing served political and cultural purposes in various historical periods. It no longer serves the evidence. The Babylonian contribution to what became Greek mathematics, and through Greek mathematics to the entire Western scientific tradition, is a question that the evidence demands be taken seriously. Not as an argument that Greece gets no credit, but as a recognition that credit assigned without historical accuracy is not credit at all. Mathematics built on borrowed foundations is still mathematics. The Greek contribution of formal proof, of deductive argument, of the axiomatic method was genuine and transformative. It was also built on something. Knowing what it was built on does not diminish it. It makes it more real. In the spring of 1900, a group of Greek sponge divers returning from North Africa encountered a submerged reef near the small island of Antikythera, beneath the Peloponnese and Crete. They dove to investigate and found a Roman-era shipwreck on the seafloor, carrying the remnants of what appeared to have been a large cargo of artworks and luxury goods. Bronze and marble statues, glassware, amphorae, and several lumps of heavily corroded bronze that looked, at first inspection, like fragments of the hull or its fittings. The divers brought everything up. The lumps of bronze sat in the National Archaeological Museum in Athens for nearly 2 years before anyone looked at them carefully enough to realise they were something else entirely. What the lumps of bronze contained was a geared mechanism of extraordinary complexity, a device built from at least 30 interlocking bronze gears of varying sizes, housed in a wooden case no larger than a shoebox, with inscriptions on its faces describing its functions and dials on its surfaces showing its outputs. When the device was intact and operational, turning a single input shaft would cause all the gears to move in their defined relationships, driving the output dials to displace the position of the sun and moon in the zodiac, the phase of the moon, the timing of the next solar and lunar eclipse, the positions of the 5 known planets, and the schedule of the major Panhellenic athletic games. It was, in the most literal and precise sense, a mechanical computer. It was built somewhere between 260 BCE. The Antikythera mechanism has attracted enormous scholarly and popular attention since its significance was recognized in the 1970s, when X-ray imaging first revealed the full complexity of its gear train. What has attracted considerably less attention is the specific source of the astronomical knowledge embedded in its design. The gear ratios in the mechanism encode specific period relations, mathematical relationships between the cycles of celestial bodies that determine how many rotations of one gear correspond to one rotation of another. These period relations are not original to Greek astronomy. They are Babylonian. The Saros cycle, used by the mechanism to predict eclipses, is a Babylonian discovery, documented in Babylonian astronomical records centuries before the mechanism was built. The period relations for the planets encoded in the mechanism's gear ratios match. With a precision that cannot be coincidental, the Babylonian astronomical parameters that have been refined over generations of systematic observation and tabular computation. The mechanism is Greek engineering. The data it encodes is Babylonian astronomy, the logical architecture that connects the two. The understanding that celestial periods can be represented as gear ratios, that a mechanical system can be made to model the mathematical relationships in an astronomical prediction table by translating those relationships into physical dimensions, is a conceptual bridge that somebody built. That bridge is the missing link. No Greek text survives that describes the theoretical basis of the mechanism's design. No treats explaining how to translate astronomical period relations into gear specifications has been found. The mechanism exists, fully formed and operational. Its theoretical foundations are absent from the record. The hypothesis that suggests itself, that the theoretical foundations of the Antikythera mechanism were transmitted from the Babylonian astronomical tradition to the Greek engineers who built it, through channels that left no surviving written record, is not provable on current evidence. It is, however, the simplest explanation for a gap that is otherwise inexplicable. The mechanism's astronomical parameters came from Babylon. Its mechanical form came from Greek craftsmanship. The idea that you could build one from the other came from somewhere. The 500,000 unread tablets may yet tell us where. The Babylonian convergence on binary adjacent encoding did not happen in isolation. Across the span of human history, the same structural insight, that information can be represented using a minimal set of distinct states arranged in positional sequences, has emerged independently in contexts so different from each other that common transmission is implausible. This pattern of independent convergence is itself a kind of evidence, and it points toward a conclusion about the nature of computational thinking that is more interesting than any single historical claim. The I Ching, the ancient Chinese classic of divination, is structured around a system of 64 hexagrams, figures composed of 6 horizontal lines, each of which is either broken or unbroken. The broken line represents one state, the unbroken line represents another, and the 6 lines are arranged in an ordered vertical sequence. Any of the 64 possible combinations of 6 binary positions can be represented in this system. Mathematically, this is identical to a 6-bit binary number, a positional sequence of 6 binary states, capable of encoding 64 distinct values. The I Ching encodes a universe of meaning in exactly the same information theoretic structure as a byte of computer memory. In the 17th century, Gottfried Wilhelm Leibniz, who is credited in Western mathematical history with the independent invention of binary arithmetic, encountered the I Ching through Jesuit missionaries who had studied it in China. Leibniz recognized immediately that the hexagram system was a representation of the same binary principle he had been developing from a purely mathematical direction. He wrote about the connection with evident excitement. This philosophical principle he had derived through logical analysis, that all numbers, all information, all reality could be encoded using only unity and the void, 1 and 0, had been embodied in a Chinese text of extraordinary antiquity. 2 entirely independent traditions had arrived at the same structure, and both of those traditions had a predecessor, or rather, a parallel, in the clay tablets of ancient Babylon, where the 2-symbol positional notation and the discrete sequential logic of computation had been embedded in mathematical practice for centuries before either the I Ching or Leibniz. The 3 traditions did not know about each other. The Babylonian scribes were not reading Chinese divination texts. Leibniz was not consulting Babylonian clay. The convergence is structural, not historical. It happens because the principle being discovered is not a cultural artifact, but a mathematical truth. a property of information itself that any sufficiently rigorous intellectual tradition, pressing toward precision and efficiency in the representation of structured data, will eventually find. This is the deepest implication of the pattern traced across this documentary. The appearance of binary logic, iterative algorithms, positional encoding, and conditional branching in ancient Babylonian mathematics is not evidence of ancient wisdom uniquely ahead of its time. It is evidence of the universal character of these computational principles, of the fact that they are not inventions but discoveries, waiting in the structure of mathematics itself for any mind that approaches the problem of information with sufficient care. The Babylonians were careful, they were systematic. They pressed the problem of reliable computation in every direction they could reach. And they found the same answers that every other tradition has found when it pressed the same way. The answers are always the same, because the answers are true. There is a word that every person who has ever typed a search query, asked a question of a voice assistant, or watched an algorithm curate their social media feed has used without knowing its history. The word is algorithm. It comes from the name of a 9th century Islamic scholar who worked in the House of Wisdom in Baghdad, a scholar known in the Arab world as Al-Khwarizmi, which translates roughly as the man from Khwarizm, a region in what is now Uzbekistan. Al-Khwarizmi wrote a treatise on mathematical calculation that became the most influential mathematical text of the medieval world, translated into Latin, read across Europe, and used as a primary textbook for centuries. The Latin transliteration of his name, algorithmi, became the word for the systematic mathematical procedures his text described. The word is one of the most common in contemporary technological vocabulary. Most people who use it have no idea where it comes from. Al-Khwarizmi built his mathematics explicitly on the Greek tradition. The same Greek tradition that Neugebauer's research showed was built on Babylonian foundations. The chain of transmission from Babylon to the present is not speculative. It is documented at every link. Babylonian mathematics passed to the Greek world through the contacts described in the preceding chapter, through the travels of Thales and Pythagoras, through the Hellenistic synthesis that followed Alexander's conquest of Persia and Babylon, through the astronomical tradition that carried Babylonian period data into Greek science, via the path of the Antikythera mechanism, and the great astronomical syntheses of Hipparchus and Ptolemy. Greek mathematics passed into Arabic scholarship through the translation movement of the 8th and 9th centuries, when the House of Wisdom in Baghdad systematically translated the entire corpus of Greek scientific knowledge into Arabic. Al-Khwarizmi worked in that tradition. His name became the word for what it produced. From Al-Khwarizmi, the chain continues through the medieval European universities that adopted his texts as the foundation of their mathematical education, through the Renaissance mathematicians who built on Arabic foundations to develop the algebraic methods that would eventually produce calculus, through Leibniz and Newton and Boole and Shannon. Each link in this chain is documented. Each step of transmission is recorded. The conceptual architecture of modern computing, the binary logic, the positional encoding, the iterative algorithm, the conditional branch, was not invented in Silicon Valley. It was inherited there, through a chain that stretches back through every major intellectual tradition of the intervening centuries to the clay tablets of ancient Babylon. What the smartphone in your pocket computes. It computes using operations that are conceptually identical to operations documented on Babylonian tablets 4,000 years ago. The substrate has changed, from fire clay to semiconductor memory, from read marks to electronic states. The logical architecture has not changed in any fundamental sense. Discrete states, positional values, sequential operations, iterative procedures, conditional branches. These are not the features of a particular technology. They are the features of computation itself, found first in clay, implemented now in silicon, waiting to be implemented in whatever comes next. Some of the computational methods developed in ancient Mesopotamia did not pass into the present through the chain of transmission described in the previous section. They arrived there independently, rediscovered by mathematicians and engineers who had no knowledge of their ancient predecessors, because the methods in question are sufficiently useful, and the mathematical principles underlying them sufficiently fundamental that anyone who approaches the relevant problem seriously will eventually find them. These are the living algorithms, procedures so well matched to the problems they solve that they have not merely survived but recurred. The iterative square root procedure documented on YBC 7289 is perhaps the clearest example. Newton's method, formalized in the 17th century, is a generalization of exactly this procedure, a framework for applying the same refine and repeat logic to the approximation of any function's root, not just square roots. Newton arrived at this by mathematical analysis, following the logic of the problem wherever it led. The logic led him to a procedure that the Babylonian scribe on YBC 7289 had already been using 18 centuries earlier. The algorithm was not transmitted from Babylon to Newton. It was rediscovered because it is correct. The Quake game engine's fast inverse square root, a celebrated piece of computational optimization from 1999, is a refinement of the same basic iterative approach, applied now to three-dimensional graphics rendering rather than to clay tablets, running billions of times per second on hardware that its ancient predecessor could not have imagined. Lookup tables appear throughout modern computing in exactly the form that Babylonian scribes developed them, as pre-computed arrays of values that allow a program to retrieve a result rather than compute it fresh each time it is needed. The trade-off is the same as it was in ancient Mesopotamia. Storage space exchanged for computational speed. And the technique is used wherever that trade-off is favorable, which is wherever the same computation must be performed repeatedly, and the values can be determined in advance. Trigonometric lookup tables were standard in scientific computing before floating-point processors became fast enough to compute trigonometric functions in hardware. They remain standard in embedded systems where computational resources are constrained. The base 60 system designed for clean fractional division underlies every angular measurement in the modern world. Latitude and longitude are expressed in degrees, minutes and seconds. Base 60 subdivisions of the degree, chosen because they divide evenly by the most common fractions encountered in navigation and surveying. Astronomical coordinates use the same system. GPS satellites transmit their position data in degrees, minutes, and decimal seconds. Every map application on every phone in the world represents location using a coordinate system whose architecture was designed in ancient Mesopotamia for the specific computational advantage of clean fractional division. The Babylonians made this choice for a reason. The reason was correct. The choice has never been superseded. The clay is gone. The algorithms are alive. The medium has changed in every possible way, from fired earth to glass, and metal and silicon and light, from read marks to electronic states, from tablets carried under a scribe's arm to signals transmitted at the speed of light between computers on opposite sides of the planet. None of these changes have altered the underlying structure. The operations that ancient Babylonian mathematics identified as the necessary tools for reliable computation are still the operations that reliable computation uses. This is not coincidence. It is mathematics. Draw back from the specific historical claims and the particular tablets and the individual scholars, and a larger picture becomes visible. Every major theme of this documentary, the two-symbol positional notation, the iterative approximation algorithms, the pre-computed lookup tables, the conditional logic of the omen texts, the colophon-based provenance system, the structured pedagogical resources of the Aduba, resolves, at the level of its deepest structure, to the same underlying observation. The human brain, given the problem of processing information reliably and at scale, converges on a small set of architectural solutions. These solutions are not culturally specific. They are not technologically contingent. They are properties of the problem itself, which means they are properties of any solution that actually works. The minimum number of states required to carry information is 2. This is a mathematical theorem, not a historical accident. Any system, neural, mechanical, electronic, ceramic, that encodes information in binary states is not making a culturally arbitrary choice. It is implementing the minimum sufficient information-bearing architecture. The Babylonian two-symbol notation, the Chinese hexagram system, and the electronic transistor are all implementations of the same architectural minimum. They arrived there by different paths. They arrived at the same place because there is only one place to arrive. The most efficient framework for representing large quantities with a small symbol set is positional notation. This is also a mathematical fact, not a design convention. A positional system with k symbols can represent any quantity to n digits using kn states, an exponential gain over systems that represent magnitude directly in the symbol rather than in its position. The Babylonian scribes chose positional notation for the same reason that computer architects chose positional notation for binary integers. It is the most compact and efficient encoding of numerical information in a discrete symbol set. The choice was not transmitted across the millennia. It was re-derived independently because the mathematics made it necessary. Version control, lookup tables, test suites, conditional branching, iterative computation. Each of these practices solves a specific recurring problem in the reliable processing and transmission of structured information. Each was developed in ancient Babylon as a response to practical necessity. Each was redeveloped in the modern era as a response to the same practical necessity encountered in a different technological context. The problems are the same because human cognition has not changed. The solutions are the same because the problems have not changed. And the solutions are the same because they are correct. Not locally correct, not correct for the time, but universally correct, derivable from first principles by any intelligence that takes the problems seriously enough. The Babylonian scribes were not ahead of their time. This framing, flattering as it seems, is actually a form of condescension, a way of acknowledging remarkable achievement while safely relocating it to a category of historical curiosity rather than genuine precursor. The Babylonian scribes were doing what minds do when they think clearly about problems of information. They were finding what is findable. The algorithms they developed are not traces of ancient genius. They are landmarks in the territory of mathematical truth, found 4,000 years ago by people navigating that territory with nothing but their intelligence and their clay. There is a storage drawer in the British Museum that contains a clay tablet which has not been read by human eyes since the city in which it was made ceased to exist. The city may have been Nippur or Sippar or Babylon itself. The acquisition record is incomplete, the provenance uncertain. The tablet is catalogued by number and approximate date and general content category. Its specific contents are unknown. It has been waiting in that drawer, or in drawers like it in other institutions around the world, for somewhere between 2,000 and 4,000 years. This is not unusual. There are hundreds of thousands of such tablets. Each one was made by a person who woke up on the day of its making, prepared their clay, selected their stylus, and pressed marks into wet earth with some purpose in mind. The purpose might have been trivial: a record of a grain delivery, a receipt for a silver payment, a note about a boundary dispute. Or it might have been something else: a mathematical procedure, an astronomical prediction, a structured information resource designed to be used by the specialists who followed them. Most of the trivial tablets have been read. The mathematical and astronomical ones, the hardest to translate, are disproportionately represented in the untranslated remainder. The portion of the corpus most relevant to the argument this documentary has made is the portion most likely to be still waiting. What the unread tablets might contain is, by definition, unknown. But the pattern of what the translated tablets have already yielded, the parametric algorithms, the positional encoding, the iterative procedures, the conditional logic, the version control, suggests that the untranslated portion is not likely to be less interesting. The tablets we have found were not selected for their significance. They were selected by accident. A random sample of 4,000 years of systematic intellectual work at the highest level of a civilization's knowledge production is not likely to have exhausted the interesting material in its first 5%. The clay asked the question first. It asked, what is the minimum architecture needed to encode, store, and process any information reliably? It pressed the answer into fired earth over the course of 2,000 years of patient, careful, institutionalized intellectual work, and then it buried that answer in the soil of the Near East, where it waited for someone to find it and ask the same question. The transistor is the modern answer to the same ancient question: binary notation, positional encoding, iterative algorithms, conditional logic, version control. The clay got there first, not because anyone in ancient Babylon planned it that way, but because the question had only one right answer, and minds that ask the right question clearly enough tend to find it. Somewhere in those storage drawers, the answer is still being given. The machines that are now learning to read it will open tablets that have been sealed for millennia and find, pressed into fired clay by hands that turned to dust 3,000 years ago, instructions that still work, procedures that still terminate, algorithms that still converge. The software running on your device tonight does not know it is descended from clay. It does not remember the reed that pressed the first mark. It does not carry any record of the scribe who pressed it, or the city that surrounded the act, or the civilization that built the institution that trained the scribe to press the mark correctly. But the logic is the same logic. The structure is the same structure. The mathematics is unchanged.